So thank you for letting me present this article. So today I will talk about approximating, covering, and minimum enclosing balls in hyperbolic geometry. So this is a joint work with Frank Nielsen. So let's define the minimum enclosing ball problem. So finding the smallest enclosing ball, or minimum enclosing ball, consists in finding a ball which contains all points of a given point set, P, and such that the ball has minimal radius among all of those balls. So we can translate this by main max formulation on the center C of the ball. So here we can find a little example in the Euclidean setting. So when we consider the Euclidean distance for this finite point set, we obtain this finite enclosing ball. So we will denote it by MEB. So in the Euclidean setting, this problem is well defined since we have uniqueness in existence of the center C star and of the radius R star of the MEB. But this problem is computationally intractable in high dimensions. And thus we have to focus on approximate methods. And thus we relax the condition of wanting the best approximation, of wanting the best radius, and augment slightly the radius allowed. So we will search for 1 plus epsilon times R star balls. So approximate solution has been given in the Euclidean case, and one is the Bader-Yu and Clarkson's algorithm, which consists in repeating the following procedure, which we start with a point C belonging to the point set P, and just move towards the farthest point from C in order to get another center for the ball. But how can we deal with point set whose underlying geometry will be not Euclidean? So responses have been given in two different settings. One is for dually flat manifolds, which has been done by Nock and Nielsen, and another setting is for Riemannian manifolds, and this has been treated by Arnaudot and Nielsen in 2013. So since the hyperbolic geometry comes from Riemannian manifolds, we can apply those results and give some existent theorem, but we cannot have any explicit bounds on the number of iterations, nor we can assume that we are able to precisely cut geodesics. So our contribution is the following. We expose a closed form formula to compute alpha midpoints, which is like the generalization of barycenters. And so with this, we can find an intrinsic epsilon approximation algorithm in order to solve the minimum enclosing ball problem. And we also guarantee 1 over epsilon square convergence time. And we also can devise some clustering algorithm using this MEB algorithm as a black box. So we start with the model of di-dimensional hyperbolic geometry. So this is the Poincaré ball model, which is in fact the units ball, the dimensional unit ball with the hyperbolic distance rho, which is given as in the formula. And we have a Riemannian metric which is induced by this distance. So we have to generalize shortest path between 2 points, which is called like geodesics. So in this setting, geodesics can be seen either as straight Euclidean lines which passes through the origin, or as circular arcs which are orthogonal to the unit sphere. And we also have to consider balls in this model. So circles or balls look like Euclidean circles, but with their center which has been shifted. So here is like an example where the red ball is the MEB, the hyperbolic MEB, while the blue one is the Euclidean MEB. And we also see the difference between the real center, the Euclidean center, the pink cross, and the red one, which is it's a true center. If we can consider transformation of this plan or ball, and we just consider translations which are given by the formula in either dimension. And thus, with this, we can devise a alpha midpoint calculation for every 2 points P and Q. So the alpha midpoint is the generalization of the barycenter. And so M has to belong to the geodesic which joins the points P and Q and must verify a relation with the distances. And if we notice that in the special case P, which is equal to the origin, and Q belongs to the x-axis, we also notice that the alpha midpoint lies on the x-axis too, and we can compute it directly, its coordinates, by the following equations. And we can obtain a formula which is available for every pair of points in the unit ball by using some symmetry invariance of the distance and using also translations to resolve to return to the preceding case. And by doing this, we obtain a closed form formula for computing the alpha midpoints, which is linear in the dimension. And furthermore, all these transformations are exact in the sense that they just involve square roots and rational transformations. So here is the algorithm for a ball with fixed radius r. So now we just change a little the first condition by allowing by searching enclosing balls of radius 1 plus epsilon times r. And this is given by the following algorithm. So I had a little demonstration, but and this consists in, we start with a point, and each time we can see in P a point which do not belong in this sphere with center C and with radius 1 plus epsilon times r. We just move towards this point until the sphere or ball of radius r touches this point. And we continue until every point has been, until there is no more points lying outside the ball. So it's a rather straightforward application and generalization of the preceding algorithm. And the idea of the proof is just to consider this certain update of CT, which is the current center. And by saying that the theta prime angular is obtuse, by applying the hyperbolic law of cosines, we easily obtain a bound for the number of iterations. And so we proved that the enclosing hyperbolic ball of radius r algorithm can be solved in a 1 over epsilon square time. And moreover, we know the big O constant, and this constant is equal to 4. And we can also wonder what is the error between our approximation and between the real MEHB center, and this is given by this formula. So as we normally in general do not know R star, the EHB algorithm in fact returns more than just an 1 plus epsilon approximation, because in the case where R is inferior to R star, the result obtained, which will be that R should have been less than R star if after 4 epsilon iterations we still haven't obtained a good approximation. And so we implement this with a dichotomic search on the radius in order to obtain the real minimal hyperbolic enclosing ball. And this algorithm require big O of n over epsilon squared times log of 1 epsilon over epsilon iterations to finish. So here is the algorithm. So we just see that it's a dichotomic search where we have to treat the case whether or not the first algorithm has converged. These are our experimental results. So as we could foresee, the number of iterations do not depend on D. So these curves are the number of alpha midpoints calculations as a function of epsilon in both in logarithmic scale. And so we see that it does not depend on D. And by plotting the running time, we see that the slope is approximately -2, which means that the running time is approximately in big O of 1 over epsilon square. And we see that changing the dimensionality of the data just produces vertical translation in this logarithmic scale. As applications, we can just apply these to data whose structure is hyperbolic. And this is the case for known subfamilies of normal distributions, such as the location scale family, which is just n-variate normal distributions, but with the scalar covariance matrix. We can also consider the case where the covariance matrix is diagonal. So both those cases are just metric space with a hyperbolic metric. And we can also consider the subfamilies of fixed mean d-variate normal distributions. So as when considered as statistical manifold with their induced Fisher information metric, these spaces are hyperbolic. So here is a little example with just two-dimensional location scale families. So on the right, this is the mu sigma plane coordinate, a half plane. And on the left, we have a representation of each plane as a distribution. And so we see that for instance, the E point, the pink curve, it lies on the geodesic between the green and blue one. And we can notice that it has a slightly more greater standard deviation. And in red figures the center of the MEHB, of the 3 points. So we can use also this algorithm as black boxes in order to compute cluster centers. For instance, if we use it in the approximation algorithm given by Gonzalez, we could obtain both algorithms for solving covering in hyperbolic spaces. So covering consists in finding the minimal number of balls of radius R, which can cover the entire point set. And we can also solve the K-center problem in this with this time computation. And the K-center problem consists in finding the best radius for K balls in order that these K balls cover the entire space within an approximate factor. So here is the Gonzalez for the first reversal approximation algorithm. So it's just a greedy algorithm which tries to compute which successively splits one cluster into several clusters. So one of the opening is concerns the core sets in hyperbolic geometry. So when we compute, for instance, an enclosing ball in hyperbolic geometry, we see that only a few points are really useful in the computation, which are the balls which lies near the surface of the ball. And so this is defined like as an epsilon core set, and there are fundamental differences with the Euclidean setting, since it has been proved that core sets are size at most 1 over epsilon by Badiou and Clarkson. So here is like some thought for further research. I really thank you for your attention.